So let's talk a little bit about UV spectroscopy. I want to start off by reminding us about the electromagnetic spectrum. If we look at the electromagnetic spectrum, on one end we have these gamma rays, and the gamma rays have a very short wavelength. And we transition to things like UV, and then there's the visible region, and then IR, and on the other extreme we have radio waves, which are very long wavelengths. And if you look at the energy of these things, a short wavelength is going to have a really high energy wave. And on the other extreme, the radio waves are going to have a very low or lower energy wave. So what we have, if we look at the energy of the wave, this is proportional to the inverse of our wavelength. So as the wavelengths get shorter and shorter, we have a higher and higher energy wavelength. As they get longer and longer, we get a lower and lower energy wavelength. That's going to be important when we start to look at a topic like UV spectroscopy. So what exactly is happening in UV spectroscopy? Well, what we're doing in UV spectroscopy is we're taking a conjugated system, and then we're going to be shining light on this. And we're going to be measuring some kind of absorbance. So what kind of energy is being absorbed by this system? If you remember from our discussion of MO theory, we have 4 atomic orbitals that are contributing to this pi system. That means that we're going to have 4 molecular orbitals that come out of this system. Now we don't need to really know what the structure of these are, but if we have 4, that means we have a psi 4, psi 3, psi 2, and psi 1. And here we have an increase in energy. And we can look at the electrons that are in these systems. 4 atomic orbitals gives us 4 electrons in the system. If we pair them up, only psi 1 and psi 2 are going to have the electrons in them. These are our bonding molecular orbitals. Psi 3 and psi 4 are our anti-bonding molecular orbitals. So we can identify some key things here. The psi 2 in this case is the highest occupied molecular orbital, or HOMO. And then the psi 3 in this case is the lowest unoccupied molecular orbital, or LUMO. Now what's happening in UV spectroscopy is we are going to shine light on this system, and one of these electrons that's in our highest occupied molecular orbital is going to get promoted to a higher energy state, either the psi 3 or the psi 4. So what we start off with is something called the ground state, and after we shine light on this, we end up with an excited state. So we could have a case like this, where now one of those electrons that was in psi 2 is now sitting in psi 3. So that energy was being absorbed by the system, and that electron was promoted up to that higher energy state. Now this electron can transition back down to its original energy state, and there's a couple different processes that can happen in this case. It could give off light. So that's one thing that can happen, give off light, or depending on how that transition works, there could be different types of energy that are being released. So this is going to give off that energy in some way. Often it's in the form of light. But for UV spectroscopy, we're measuring that absorbance. We're measuring the difference in these energy transitions. How easy is it for us to take an electron and promote it up to a higher energy state? The key difference there is, what is that energy difference that we're looking at? So the energy difference is really the difference in energy between the lowest unoccupied molecular orbital and that highest occupied molecular orbital. So something that we call the HOMO-LUMO gap. The HOMO-LUMO gap. That energy difference is proportional to the difference between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. Now, how is this HOMO-LUMO gap impacted by the conjugated systems that we see? So let's take a look at some different conjugated systems and see what happens to that HOMO-LUMO gap. So if we take something like ethylene, and we're going to compare that to butadiene, and we're going to compare that to a hexatriene in this case. So what we see is that lambda max, or the maximum wavelength that we see, this is a shorter wavelength, and as we go down this table, it gets longer and longer. So as we go down this table, the increase in conjugation leads to an increase in that lambda max, or the wavelength of that max absorption. So what does that tell us about the energy then? What does it tell us about the energy of that absorption? So a shorter wavelength means that this is going to be higher energy. And the longer and longer the wavelength gets, the lower and lower the energy gets. So if we increase the conjugation, we've increased the lambda max, and we have lowered that energy. So that energy that we're looking at here, this is that HOMO-LUMO gap. So that's telling us that if we increase the conjugation, we are decreasing that delta E corresponding to that HOMO-LUMO gap. So that means in our molecular orbital picture, the energy difference between those orbitals is getting closer and closer. So if we have a longer and longer conjugated system, then it's easier, it takes less energy for us to transition electron from that ground state up into that excited state. And we can see that difference by noting the longer wavelength, or by measuring the actual energy associated with that wavelength. So hopefully this information is useful when you start to look at some of the differences in the molecules that we look at. So we start to try to solve some of the problems associated with this UV transition.